Hello, our project is the Industrial Animatronic Robot. Meet the team. I'm Austin, the electrical engineer. We also have Armando, the computer engineer, Melvin, an electrical engineer, and Tony, an electrical engineer. The background and motivation. In today's world of modern engineering and entertainment, animatronics bring together creativity, technology, and innovation. They captivate audiences and push the boundaries of what machines can do. From theme parks to museums, theater shows to public displays, animatronics have become a powerful tool for storytelling, blending lifelike movement with interactivity to create immersive, unforgettable experiences. Our project dives into this fascinating world by designing and building an animatronic robot. Using industry-standard technologies like programmable logic controllers, or PLCs, and human-machine interfaces, or HMIs, we aim to contribute meaningfully to the field of animatronics and robotics. What drives us? The desire to combine engineering skill with creative expression. We're building more than just a robot. We're building a platform that educates, entertains, and inspires.
So for this project, our main goal is to design and build a functional robot that can demonstrate both movement and interaction. So we basically just want to integrate concepts of electrical and computer engineering into one project. For movement, we want to implement servo motors to make it seem lifelike and responsive. We're going to be making our own PCB, and as you can imagine, this reduces the wiring complexity. And we're going to be ensuring reliable power using voltage regulators, as we'll discuss later, and circuit breakers to protect the more sensitive components. We want to develop an intuitive HMI, basically something that's just simple, that can easily command or trigger movements. And for testing, we want to focus on validating the full system. This includes debugging the subsystems individually, making sure everything works together before the final demonstration. So for this slide, we have our engineering specifications. We're going to be focusing on three main specifications of testing, including fault response time of less than a second, number of axes, 3 minimum, and the HMI activity being able to read and write. But we do have other specifications as well included. We have an operating voltage of 24 volt DC with the maximum operating current of 5 amps for our protection and control system. For the HMI itself, it's operating at 12 volt DC and uses up to 1 amp, and it supports LCD and OLED displays. And it communicates through Ethernet, Modbus, and can have controls like selector switches and push buttons, and a built-in e-stop. Also, the animatronic itself is running at 12 volt DC with 2 amps per axis and supports at least 3 axes. And ideally, we want it to stay under 1 watt per axis. This is our system level hardware diagram, which shows how all the major components are connected and interact with the robot. On the left side, inside the control panel, we start with a standard 120 volt AC input, which gets stepped down and regulated by our power supply block to deliver appropriate DC voltages. The power is then distributed to the PLC, motor controller, protection circuitry, and HMI. The PLC, which is our central control unit, is responsible for sending movement commands, receiving sensor data in real time. We've also built in protection components like fuses and circuit breakers across the system to isolate faults and prevent damage. On the right, you can see the animatronic robot, which includes a custom PCB and a motor control and sensor breakout board, which interfaces directly with the servo motors. The color coding also maps each subsystem to a team member's responsibility, so everybody has a clear role in development and troubleshooting. This is our system level hardware diagram, which shows how all the major components are connected and interact with the robot. On the left side, inside the control panel, we start with a standard 120 volt AC input, which gets stepped down and regulated by our power supply block to deliver appropriate DC voltages. The power is then distributed to the PLC, motor controller, protection circuitry, and HMI. The PLC, which is our central control unit, is responsible for sending movement commands, receiving sensor data in real time. We've also built in protection components like fuses and circuit breakers across the system to isolate faults and prevent damage. On the right, you can see the animatronic robot, which includes a custom PCB and a motor control and sensor breakout board, which interfaces directly with the servo motors. The color coding also maps each subsystem to a team member's responsibility, so everybody has a clear role in development and troubleshooting.
Here is our software diagram. This is a no fault condition state. So Basically, the control flow is that we're going to push a button to start the profile. If there is no active fault, then the profile will start. We're going to use what's called a state machine, which is going to continually increment position states. And throughout the position state incrementation, we will constantly check the sensors to see if a fault occurs. If a fault ever occurs, we will enter a faulted state where everything will stop. If not, we will continue until we reach the maximum state, in which case we will know that the program was successful, and then we will return to a home, and then it will be able to be push started again.
Moving on to the hardware selection, we had a few options to choose from when it came to selecting an MCU. The MCU will need to fulfill tasks such as motor control, communication protocols, and real-time responsiveness, so selecting the right controller is crucial to the project. So ultimately, we did choose the SAMD21, which is the one that is highlighted. Uses a 32-bit ARM core and runs at 48 megahertz and gives us 32 kilobytes of RAM, which is more than enough for what we're going to be using for the control logic. It also supports multiple communication protocols like I2C, SPI, and UART, which are essential for TTL communication with our motor control PCB. Having decided on the SAMD21 family for the microcontroller, the next crucial step was selecting the specific variant. This slide illustrates our comparison between the SAMD21E, the SAMD21G, and the SAMD21J. There was a heavy emphasis on critical features like the number of I/O pins and ADC channels, which are essential for not just controlling the animatronics functions and sensor integration, but also it provides scalability for the project. So the SAMD21E has 20 I/O pins and was simply just too limited for the numerous servo controls and general purpose signals that the animatronic requires. On the other hand, the SAMD21J, while it is powerful, it offered 52 I/O pins and 20 ADC channels, which is way more than we actually need. This would have introduced unnecessary complexity and cost without providing actual benefit for this application. So ultimately, we did go with the SAMD21G, which is integrated into the custom PCB. It has 38 I/O pins, and it provided the perfect balance. It has ample connectivity for all the motors, the custom TTL communication, and other essential signals without any excess. Now we needed to select the right motor type, which helps achieve the desired movements of the animatronic. Our primary needs were high precision, consistent torque, and smooth, repeatable motion across multiple axes. We evaluated stepper motors, and while they have a tendency to lose torque at higher speeds and have a proneness to stalling, there is a function for the animatronic that runs at low speeds that will only require moderate torque at most. So we chose to have a stepper motor, although not implemented across multiple functions. There are standard servo motors, which offer good control for simpler tasks, but their typically limited motion range and less robust torque maintenance were not ideal for all the complex dynamic joints in the animatronic. So contrary to standard servos, we chose closed-loop servo motors with integrated drives, and as the table highlights, they offer very high precision due to real-time feedback and error correction via PID adjustment. This, combined with the high and scalable torque, is absolutely essential for the nuanced dynamic movements of our animatronic. While they do involve a higher cost and more complex setup, the superior control, accuracy, and reliability they provide for critical animatronic motion made that the clear choice for controlling multiple axes of the animatronic. For the servo motor selection, we were able to secure a sponsorship with the company Robotis, who provided several Dynamixel servo motors, including the Dynamixel XC330T288T, the Dynamixel 2XL430 W250T, and the Dynamixel XL430 W250T. Moving on to sensor selection, accurate feedback is needed for both precise motion control and robust safety for the animatronic. We did evaluate a range of sensor types to fulfill the distinct roles. So first, encoders were fundamental, as highlighted. Their ability to track motor rotation with high resolution and digital pulses is indispensable for the closed-loop position and speed control of the servo motors. They do ensure smooth and accurate movements for the animatronic. And equally vital are limit switches. These are simple, fast, and precise mechanical contacts that are essential for detecting end-of-range motion. They serve as a sort of critical safety measure, preventing unintended collisions and mechanical overextension for the system. It's a key part for the redundant safety. And while other sensors like the proximity sensors, optical sensors, Hall effect sensors, and ultrasonic were considered for very specific applications, for the core motion control and safety, for the animatronic encoders and limit switches provided the most reliable and direct feedback needed. The combination of these two ensures that we have real-time data for both dynamic animation and critical system safeguarding.
Hardware technology comparison selection. So for this project, we're going to be using what's called a PLC, programmable logic controller. The reason we're using this instead of a failsafe or a safety relays is that the cost to performance ratio is just not really in the budget for this project, and we will get lots of protection using a PLC. Hardware part comparison. So in specific, the PLC we will be using is the 800 series, Micro 800 series Allen Bradley's. This is really the only option because the price is low and the software is free.
So looking at the different types of voltage regulators we had to choose from, we have buck boost, linear voltage regulators, and switching regulators. Our project requires stepping down from a higher voltage source, so we were looking primarily at buck converters. They're efficient, very efficient, about 85 to 95%, and they generate relatively low heat, usually under half a watt. They're also, pretty simple to work with. It means like they have fewer components, easier PCB layout. Um, the buck boost regulators, they offer flexibility in voltage direction, but they come with higher complexity, sometimes more heat dissipation. Linear regulators are the simplest and cheapest, but they're also the least efficient. Um, and switching regulators give us versatility and decent efficiency, but they can get pricey. So we just ended up going with buck. As for choosing a voltage regulator to work with, we have a few different choices in terms of buck converters. We evaluated them based off voltage range, output current, efficiency, cost, and overall suitability for our design. We ended up going with the LM2576 as we need to convert from a 12 volt to 5 volt DC, and obviously it supports that. It can support a wide range of input voltage. It can handle 3 amps of output current, and it provides excellent thermal reliability, and it's very available and cheap. Um, just seems the best balance of performance and simplicity.
The human-machine interface is the central point of user interaction in our system, so responsiveness, reliability, and safety were key concerns. We compared 3 technologies: web-based HMIs, remote devices, and touch display panels. Web-based HMIs, though highly mobile, rely on a wireless infrastructure and are very vulnerable to latency, congestion, and outages, posing risk for emergency stop situations. Remote devices share similar issues, with the added drawback of needing dedicated terminals for each operator, increasing cost and complexity. The touch display panel offers a wired, low latency interface ideal for deterministic operation. Though it limits user mobility, it guarantees immediate execution of safety critical commands like an e-stop. The wired architecture also simplifies diagnostics and compatibility and avoids signal degradation or wireless interference. With reduced system complexity, consistent performance, and lower costs, the touch display panel clearly emerged as the most reliable and practical interface for our animatronic control system. Once the touch display model was selected, we evaluated HMI units based on CPU power, operating system flexibility, and cost. Windows-based HMIs, while capable, were immediately excluded for being prohibitively expensive and too restrictive in customization. Linux and Raspberry Pi based units offered similar functionality, but Raspbian stood out for its open source flexibility, extensive documentation, and excellent support for our selected software. Amongst Raspberry Pi HMIs, the ED-HMI 3010-101C provided the best value. It uses a 5-volt DC supply, includes 64GB storage, and matches the performance of pricier models like the ED-HMI 3020 and the PPC CMI5 101 without redundant features like expanded I/O or higher power requirements. It avoids the need for extra regulation hardware and fits neatly within our control cabinet. Its compact form, sufficient compute power, and full capability with Ignition Edge makes it the optimal HMI choice.
We chose the C language because, first of all, it's the one we're actually most familiar with, but also we can ensure that there's fast execution and there's direct hardware access. And then because PLCs are different, then we chose ladder logic and structured text because they're not compatible with things such as C or C++ or Python or Java. For the programming IDE, we chose the Arduino IDE because we are able to program the SAMD21 using the Arduino IDE. It was going to be really straightforward to work with, and Robotics Dynamics still provides library functions as well to be able to program the dynamics of servo motors.
To support communication between the HMI, PLC, and motor controller, we compared serial protocols like UART and SPI with Ethernet. While serial excels in point-to-point connections and minimal hardware setups, it lacks scalability. Routing messages across multiple components would require intermediate processing units, introducing latency and added development effort. Ethernet, on the other hand, supports gigabit speeds, large network topologies, and simultaneous device communication. With Cat6 cabling and a gigabit switch, we achieve low latency, high bandwidth networking that doesn't degrade over distance. Ethernet also benefits from standard protocol support and error checking, making it more robust for real-time application like ours. These advantages make Ethernet the clear winner for managing our multi-device system efficiently and reliably. Our Ethernet controller needed to support SPI communication with the MCU and handle TCP/IP networking without burdening the main processor. We compared the WIZnet W5500, the A6AX11001, and the microchip ENC28J60. The ENC28J60 lacks an internal stack and offloads all network protocol handling to the MCU, unacceptable for real-time control. The AX11001 integrates a 8051 processor, but its architecture is outdated and incompatible with our system design. The W5500, by contrast, includes a full hardware TCP/IP stack, a 32 kilobyte dedicated Ethernet buffer, and supports up to 8 concurrent sockets. It connects via high-speed SPI, supports efficient Modbus TCP communication, and integrates cleanly with our microcontroller. Its superior speed, buffer capacity, and offloading capabilities made it the definitive choice. We evaluated several protocols for device communication: Modbus TCP, Modbus RTU, and Relay-based I/O. Relay I/O offers simple binary control but lacks scalability or data structure. Modbus RTU, while widely used, is slower and is limited to about 32 devices over RS-485, a serial port. Modbus TCP, on the other hand, builds on RTU's simplicity but leverages the speed and reliability of the TCP/IP stack. It supports high-speed, concurrent communication among many devices without the need for protocol converters or additional hardware. Its compatibility with our Ethernet infrastructure and diagnostic tools made it the most suitable and scalable protocol for coordinating the PLC, HMI, and motion systems. HMI software options were categorized by function: automation, product manufacturing, and process control. Automation platforms like FactoryTalk offered advanced features but introduced unnecessary complexity for our use case. Product manufacturing tools focused on repetitive metrics and modeling, which aren't central to our animatronics behavior. Process control software, however, emphasizes real-time regulation, parameter tuning, and live diagnostics, exactly what our system requires. For the available options, Ignition Edge was chosen for several key reasons. It supports non-proprietary hardware like our Raspberry Pi HMI, integrates natively with Modbus TCP, and includes a free license tier sufficient for our needs. Moreover, our team has prior experience with Ignition, minimizing training time and accelerating development. It's lightweight, robust, and a perfect match for our system's real-time coordination demands.
So when it comes to designing our custom PCB, we have a few different software options available to us. We have Fusion 360, KiCad, and Altium. These are the main ones to use. Altium being the most expensive one, actually the one with the only cost associated with it. It's a great and free open source option, but it has a steeper learning curve as well, and it has a slightly more complex UI, especially when setting up libraries and footprints. So we just ended up going with Fusion 360 because it's something we were familiar with already, and it's free.
Here is a representation of the main board schematic. This shows quite literally the entire PCB that we have designed, everything going from the Ethernet connections with the W5500 chip, with the USB-C port, the I/O connections, the power incoming into the MCU, and the power incoming into the PCB overall. We have the motor connections as well. And this also shows how the regulator is tied into the PCB because the regulators are external to the PCB itself. Here's the overall PCB layout. You can see here that the Ethernet connection is on the top left with the W5500 chip there as well. Below that is the USB-C connection, and to the right of the USB-C connection is the SAMD21G. And surrounding the entire PCB board, you can see some terminal block connections that we can use for connecting our peripheral devices.
So here we have the schematic for our voltage regulator board, which steps down 12 volts to both 5 volts and 3.3 volts. On the left side, we're using the 5 volt, and right side is 3.3 volts. Both regulators share the same 12 volt input rail and are designed to operate simultaneously without interfering with each other. We have included mounting holes and clear labeling for both test points and outputs, which make it easier to troubleshoot during integration. You can see that the component values for the inductor and output capacitor are tuned for whether it's a higher output voltage or lower output voltage. And overall, this design just allows us to safely and efficiently power both our logic level electronics and our control peripherals without relying on separate external power supplies. So moving on from the schematic to the actual PCB layout, we can see this is kind of how we chose to design it. We have the 5 volt regulator on the left side and the 3.3 volt regulator on the right side, but they're both sharing again that common 12 volt input rail, which enters from the bottom left of the board. We paid special attention to the power trace width, making sure that the lines are wide enough to handle the expected current. We also made sure that the components are placed close to the voltage regulator. And we also, at the bottom center, we included a 4-pin header for easy output access. You can see it's labeled 12 volt, ground, 5 volt, 3.3. And finally, we also added mounting holes in all four corners for the stability of the board. Overall, it's just compact, efficient, and custom tailored to our animatronics power needs.
And here's our actual cost itemized list. So as you can see on the left side is broken up into animatronic enclosure, HMI, protection and control systems, all totaling $897. But this cost is offset by the fact that we have a sponsored project. So on the right side you can see that our sponsor has provided $450 worth of motors. So adding them together we get a total out the door cost of $1,347. Here's our in-depth work distribution table. So this is just specifying pretty much everyone's exact ownership. Once we finalized our design concept, we moved into the prototyping phase. This involved creating an initial version of the animatronic using basic materials and components to validate our ideas and identify any early design challenges. We focused on building a functional structure, integrating the core mechanical systems, and testing motion through simple actuators. This helped us refine movement, ranges, joint flexibility, and component placement before committing to the final build. After the prototype was tested, we began systematic testing, starting with individual subsystems like motors, sensors, and control interfaces. We used this stage to calibrate movement accuracy, test responsiveness through the PLC system, and ensure seamless interaction via the human-machine interface. Throughout this process, we gathered feedback, documented issues, and made iterative improvements. Each round of testing brought us closer to a stable, reliable version that performed smoothly and safely. Prototyping and testing not only helped us enhance the technical quality of the robot, but also ensured the final product would deliver the intended experience, engaging, responsive, and true to our creative vision.